Greetings and welcome once again. So my name is John Gabriel and this is New Calculus Channel, and I'm going to be addressing a comment made by one of my special subscribers called Infinitesimotel. Okay. Seems like he doesn't quite understand the concept of an abstract unit. So he says it remains true regardless of the scale size of the circle, because no matter how big or small a circle is, it remains a circle. That's not the real reason. What defines it is the same for all circles regardless of comparative size. No, what actually defines it is that the diameter acts like an abstract unit whose type and size is relevant. So I'm going to explain all these things very clearly now in this presentation, okay? So what I've done here, just to give you a quick background, is I've drawn a circle with diameter 1, and I'm listing the value of this arc here. I don't actually need numbers here at all, but I'm listing it to make it easy for you. So the value of this blue arc is this 0.647, and then of course this value here is how much is covered. It's not how much is covered in when these points are mapped to this line. They're not the same length. This is actually now pi over 4. But as we go along, this arc increases to 1, okay, and then let's move it up a bit, and then 2, okay, and then roughly 3, and then there's a little last bit here remaining, which I've copied as part of the diameter here, okay, and this is the part I'm going to be talking about, okay, so 0.134 maybe. Okay, so I got it pretty close here. 131 actually. It's 0.1314. 1314. Anyway, I don't need to get it that close. 141. There you go. 3.141 is this leftover bit when we measure it. But now here's what I want to tell you. In geometry, we can measure a circle circumference exactly. So for example, I have a video called Symmetry of the Circles, and I'll show you how you can do all 4 operations, contrary to what people who write articles on academia and mainstream tell you. Oh, you know, irrational numbers blew the fuse of the Greeks' minds. Actually, they didn't. They blew their stupid minds because the Greeks knew what they were doing, and they expected those results, by the way. They knew exactly what was going on. It's the morons who never understood the elements. But in geometry, we can measure a circle circumference exactly. Take the diameter, form a unit. In other words, how do we form a unit? All right, let's look. So if we've got a circle like this, okay, got a circle like this, we form the diameter. So this diameter becomes a unit, right? So we say the measure of this ratio is 1, okay? And then, of course, the measure of this ratio is 2, etc. Okay, so now we can name these things as we move along. 1, 2, 3, right? So it doesn't really matter what size circle you have. If you have a bigger or a smaller circle, you can still call your abstract unit by simply taking the measure of this ratio, okay? The measure. I didn't write measure properly, but you know what that is. So it doesn't matter what the size of the circle is, and the leftover portion can easily be a part of the diameter of the circle, which you've considered a unit. So if you go back to this diagram here, regardless of what circle it is, when you're using the abstract unit, it's always going to be this leftover part. And how do we know? We know because if we go up here, we'll see that this leftover part is less than a quarter of the arc, right? So we can have a complete measure. All we have to do is take 3 diameters and this last remaining section, join them in a straight line, and we have the length of the circle. And by the way, Archimedes demonstrated this using spirals, okay? So he used propositions in his work, in the works of Archimedes on spirals, he shows how to do this. And I've also got an old video on this subject, so I'm not going to cover it here again. But what I'm telling you then is effectively that what algebra tries to do, okay, so what algebra tries to do is give all these a name to describe them, okay, in terms of the chosen unit diameter, okay. So this, the measure of this would in algebra would be approximately 3.14, and I'll show you now how this happens. So first of all, we sacrifice precision in algebra because we describe the measure in terms of an abstract unit. In other words, it doesn't matter what size diameter we use, we're still going to get the same answer in terms of the abstract unit. Okay, 1, 2, 3, and a little bit left over, which we still have to describe in algebra, and I'll tell you how we get to that description. But even so, we use techniques from geometry to divide the diameter into equal parts. So we can see that if we divide this diameter into 10 equal parts, and it happens to be equal to these squares, we can see that the leftover part is slightly over 1/10. And we can write that very confidently that we have approximately 3.1, right? If, okay, so my pen fell down. That's not a good thing. Let me just get it right. So if we now divide the diameter into 100 equal parts, then we can see that we're going to get 3.14, okay? And that's an algebraic measure. It's general, and because it's general, we lose precision. And I'll place a link to that Symmetry of the Circles video so that you can see how all the 4 operations are done. But even so, in order to do this, we can't just do this in algebra alone. We need geometry to know how to do this. And, oops, I don't know what happened there. Yep, okay. So this seems like a quirk with the recording software. So in algebra, we need to divide the abstract unit into equal parts. Well, we just take it on faith from geometry, by the way. It's transferred completely that it can be done from geometry. And we know that it works because any size circle produces the same answer. Similarly, we can say that it can be done with a square in its diagonal, right? So what happens here is that the methods of geometry are transferred to algebra. And we say, okay, once we divide this into an equal number of parts, and I don't know why I just moved the grid away. Okay, it doesn't give me the grid anymore. Doesn't like me. All right, never mind. So we know that we can divide it into any number of parts to get more accuracy, right? So this same concept, as I mentioned earlier, can be transferred, can be copied or transferred over to a square and a diagonal, right? I don't know if I'm still recording. Yeah, I am. Good. Okay. So if these sides are equal, we could do the same thing here. Measure 1 and then divide this part up. Divide this side up into 10 and then 100 and keep on seeing how many parts we have there. And it doesn't matter what the size of the square or the diagonal is, we get the same result. The central theme of the elements is measure, okay? Metrici, okay? Measure. In Greek, it's metrici. And you'll see the word metro and metricis and what have you repeated thousands of times in the elements, okay? Because mathematics, by the way, is the abstract science of measure and number, okay? Measure and number. And we only get to the concept of number in book 7, okay? And I want to talk about definition 1 in a moment. I will. So we use the propositions in Euclid to easily communicate these ideas. We do not need compass or straight edge, but both these tools are extremely useful. Why? Because they model the intangible objects precisely. Those objects that we're talking about, those distances, those locations, etc. Okay, so now, what does definition 1 say? So if you read definition 1, it says that a unit is that by virtue of which everything is called one. Okay, so that was just the ancient Greek way of saying the abstract unit is the measure of a ratio whose aliquot parts, are equal and assumed to be the unit. Okay, so you pick any ratio, any ratio you like with equal parts, and you can use it as the unit. It doesn't matter which one. That's why I keep on telling you that the abstract unit doesn't care about type or size. All right? So that's definition one. It took me many decades to realize that that wasn't just thrown out there. It actually makes a lot of sense. Okay, it makes a lot of sense. It is brilliant, and it took me a long time to discover that. And of course, the mainstream idiots never had a clue of what's going on. They've never understood geometry or the elements. They have no idea that the elements is about a valid systematic way of thought. It is not about geometry. In fact, the word geometry doesn't even appear in the elements. Okay, and of course, one of their main tenets is that it's based on axioms, which is total BS. There are no axioms used in the elements of Euclid. In fact, everything that the ancient Greeks did points in a direction, and there are some older writings that show that the requirements and or etimata and those things that were called axioms were two different things. And of course, they were not talking about axioms. They were talking about the requirements. Okay. So, and one of them, of course, has to be proved. The requirements have to be proved. They're not axioms. And I do that in my famous article called There Are No Axioms or Postulates in Sound Mathematics. So, finally, be careful of revision and revisionist idiots who claim that the Babylonians and Egyptians had this knowledge before the Greeks. They did not. That is a total lie. They knew nothing about trigonometry. They knew nothing about measure. I mean, measure is a central theme in the elements. Remember, the Greeks started off with line segments because they were the most common things that could be used to build a theory, to build a systematic way of thinking. Okay, so and also all fraction, arithmetic, and measure came directly from geometry using the abstract unit. You can't just say define P over Q plus R over S to be QS P S plus QR. You can't just define it, you moron. There was an old idiot that I knew once from NASA. His name was Kerry Salo. I mean, I couldn't believe what a moron this guy is. He used to teach at one of the universities. But he told me, oh, yeah, I can just define anything I want. I can define X and then just carry on building through it. No, you can't, moron. You need well-formed definitions. And for that, I give you a method to do that. The method is RASI, okay? RASI. Reification, attributes, contradictions, and independence. And that, again, comes in my article. You don't just get to define crap out of your sewer heads, okay? You need to have well-formed definitions. So that's pretty much it. I wanted to point these things out. So infinitesimal motel. I actually know your name. Maybe you don't want me to say it, so I won't. But that's what is meant by an abstract unit. Okay. That's really all it means. It doesn't mean anything else. Well, if you're not already a subscriber, become one. Follow me on Academia. I'll place a link there. Tell your friends about it. And if you're feeling generous, buy me a cup of coffee or a meal. Also, feel free to try and join our Discord. There are 10 questions. All of them are either multiple choice or true or false. So you can take the test as many times as you like. You have to get 10 out of 10 to join. My name is John Gabriel. This is a new calculus channel. Till next time.